Hello. Today I'll be discussing the typical algorithmic structure of Dynasty, which is consistent with the simulation-based dynamic user equilibrium type of DTA model. This is referred to as the DTA primer, where an entire simulation is performed and important travel time and delay information is retained. This information is then fed into a time-dependent shortest path algorithm, and a percentage of the users, especially those experiencing unsatisfactory runtimes, have their route adjusted. This newly defined path will be re-evaluated during the next iteration of the simulation. The routes and travel times are updated once the iteration is completed, and this process continues until convergence has been met and the system stops. Here is a much more detailed view of Dynasty's internal structure. We begin with a time-dependent OD table, or a vehicle roster, so there are two ways to load demand into Dynasty. We generate vehicles with the initial paths, and then we perform an anisotropic mesoscopic simulation, or AMS. We retain all the necessary measures of effectiveness, and then feed them into the next assignment. The assignment has a time-dependent shortest path algorithm, as well as a gap function vehicle-based traffic assignment algorithm, which is unique to Dynasty. After all this, we check the convergence, and if those requirements for convergence are not fulfilled, we feed the information back to the simulation component and go through another iteration. At a high level, this is consistent with the general DTA structure, just with a bit more detail. The relative gap for Dynasty is measured strictly according to the DTA primer definition. In this example, at around 20 iterations, the Dynasty gap function was reduced to below 10% at approximately 7%. That means that on average, the time for all the routes used between each origin-destination pair was at most 7% higher than the time-dependent shortest path.